afternoon, everybody. It's a real pleasure today to invite you all to this very interesting Game Changer seminar. This is number 101 that Dr. Amy Simon from NASA Goddard Space Flight Center will give. So Dr. Simon is a senior scientist for planetary atmosphere research at NASA Goddard. She joined NASA Goddard in 2001. She is the OSIRIS-REx visible and infrared spectrometer instrument scientist, and she is the project scientist for OSIRIS-Apex. She will talk to us about. She is a world expert of planet atmosphere, and she is actually the PI of one of the long-lasting, biggest solar system program, OPAL, the Hubble Outer Planet Atmosphere Legacy Program, which she was just telling us will celebrate 10 years of activity. She was the 2023 recipient of the AAS Division for Planetary Sciences Claudia Alexander Prize. And today she will discuss the mission engineering challenges and successes, remote sensing results, and early results from the sample analysis. And then we will hear a little bit about the future, because the mission is going towards a new target, the near-Earth asteroid Apophis. So let me tell you a little bit how we are going to organize, before I give the floor to Dr. Simon, the question and answer. You can see that there is a chat. Please put your questions in the chat and we will answer the questions very orderly at the end of our talk. So Dr. Simon, it's a pleasure to have you. You have the floor.
Thank you. And thank you everybody for joining us this afternoon. So as Antonella mentioned, I'll be talking to you about the OSIRIS-REx mission, which was NASA's asteroid sample return mission from asteroid Bennu. And you can see Bennu rotating in the background there of my title slide. And that is actually a combination of our shape model, so imagery and LiDAR data. And we'll talk a little bit about that as we go forward. So let's see if I can get it to advance. So OSIRIS-REx is, the name itself is an acronym. It stands for the science goals of our mission. So origins, spectral interpretation, resource identification, security, regolith explorer. A lot of words that, again, just get to what our science goals are. And so origins is that we want to understand about these asteroids, these remnants from solar system formation. So the main goal of the mission was to return a pristine sample from this very dark carbonaceous asteroid. And the other part of the mission is remote sensing. So as part of picking where we would choose our sample, we wanted to be able to map out the surface to look for composition variations on the surface, in situ resources, security. One of the main goals was to measure the Yarkovsky effect, which is this very subtle effect of sunlight pushing on the asteroid, but then as it cools off and it radiates to space, it gets pushed in a slightly different direction. Because our asteroid is a near-Earth object, understanding whether or not it presents a hazard was of great interest. And then lastly, regolith explorer, so understanding what the surface properties were like, both in support of returning that sample, but also in general for these asteroids. And so this mission was basically taking us from telescopic observations here at Earth to remote sensing from near the asteroid, all the way to bringing that sample back. So you're able to do that connection between what we see in the laboratory to what we actually find in the sample itself. Now, of course, Osiris is a very Egyptian kind of sounding name for the deity Osiris. And when we picked our asteroid, it was actually called 1999 RQ36, not particularly interesting. But we held a naming contest to name what the asteroid should be. And the winning response was from a fourth grader in North Carolina who suggested Bennu. And Bennu is a crane or a heron. It was a bird companion to the god Osiris. But the nice thing is, of course, that a bird looks quite a lot like our spacecraft, with the two solar rays sticking out to the side like wings and our sample arm kind of hanging down like a foot. And to give you a sense of scale, that sample arm is about 3 meters long. Okay, so why did we pick asteroid Bennu? And apologies that the graphic gets a little blurry sometimes. We have three types of asteroids that we're talking about here. We have main belt asteroids, that's between the orbits of Mars and Jupiter. We have Earth crossing asteroids, the red ones here, and we have Mars crossing asteroids. So this was the sort of trade space we had to go through for picking our asteroid. And what we needed to do was to sort from between them. So at the time of our proposal, there were about 500,000 known asteroids. 7,000 of them were near Earth asteroids, and less than 200 were actually optimal for doing sample return, because we not only had to get out to the asteroid, we had to bring a sample back. Of those, about 26 had a diameter greater than 200 meters. And that's because we needed something big enough that we could actually orbit and be able to take that sample. And of those, only 5 of them were carbon rich. And that's important because we wanted an asteroid that could tell us about how organics and those sorts of materials were delivered to the Earth. And so basically at the top of this pyramid, we ended up with only one object, which was asteroid Bennu. And you can see its orbit in white there and how it crosses the Earth. Now, beyond that, we did not know a whole lot about the asteroid before we got there. So we had an Arecibo observation set, very grainy there, but you could see that there was some hint of surface features. But some very smart modelers were able to make the model that you see on the upper right, which is a shape model based on that Arecibo data. From that, we had some idea that it was kind of top shaped. We knew it rotated in about 4 hours. And that shape and that rotation period led us to suspect that we would have any loose material ponding near the equator in that equatorial ridge, which would be great for sampling. So this was all we knew before we got there. Now, as part of the mission, we had a very deliberate plan on how we were going to execute this. So again, we're talking about a small object. So Bennu is about 500 meters across. That is still a microgravity environment. So the first part of our campaign was navigation. So we did what we call preliminary survey, where we did specific passes around the asteroid in different directions, as well as an orbital period around the terminator. And this was to understand the gravity field, because this was the first time we were going to be operating a mission in microgravity, but still trying to orbit. So we had to make sure we really understood how to do that. Once that phase was complete, we moved into a station keeping kind of orbit called detailed survey. And that's where we sat at the equatorial ridge location, essentially, about 5 kilometers up. And we went to different local solar times and mapped out the asteroid. So we basically let the asteroid rotate beneath the spacecraft, and we mapped up and down. And that was to build up our full global coverage of the asteroid. And that was important both for picking our eventual sample sites, but also just for scientifically understanding the differences around the asteroid. So 3 of the stations were in full daylight, the equivalent of 10 a.m., 12:30 p.m., and 3 p.m. We had 2 terminator orbits, 6 a.m., 6 p.m., and then 2 on the dark side. And this was also so that we could look at the thermal inertia of the surface using the infrared instruments. And then lastly, we moved into our sample site selection. And we had to basically pick 3 different criteria for choosing our sample sites. One was safety. So we needed an area on the surface where we could safely descend and not worry about hitting a big boulder, which could knock the spacecraft over. Sampleability, which might be a made up word, I'm not sure, but that was looking for a place where we thought we had loose material we could pick up. And then lastly, science value. So were any areas more interesting than the other? Once we finished that, we then did reconnaissance over those potential sample sites to see which ones would be best. Once we finished that, we went into what we call rehearsals. And this is probably the trickiest part of the mission. So basically, we had to leave our nice station-keeping equatorial orbit and then go over where the sample site was going to be. And we did this in stages. The first was called checkpoint, where we got to that location and then we just checked that we could match the rotation of the asteroid, so that when we came down, it wouldn't be moving to the side. Essentially, we'd be straight moving at the same rate as the asteroid. From there, we went and we did something called match point, where we slowly descended towards the surface, but did not sample. So again, we were practicing every single stage of this sample collection leading up to actually doing it. And then finally, we would do the actual sample collection. The way we had this plan, we also had backup opportunities. So we could do the sample collection attempt at least up to 3 times, and just determine if the first time didn't work for one reason or another. Was it because the sample site was a bad place, or because of something else we needed to change? So this was a very deliberate approach to try to do something that basically had never been done before. And we'll talk about the actual sampling procedure a little bit later in a minute. So in terms of samplability and safety, one thing you would have seen at that rotating model at the beginning is that every place on this surface is covered in boulders. We knew it was a rubble pile asteroid, likely the product of a collision of two asteroids in the main asteroid belt that then eventually threw Bennu out. But I think we were a little bit unprepared for exactly how rubbly it was. So what you see here is boulders of every possible shape and size and boulders on top of boulders. This is pretty much what the entire surface looks like. So that was a little bit of a surprise to us. The other thing to note is that if you look at the image on the left, you have a very dark boulder here and you have a brighter one on top of it. So you do have, boulders that are landing on top of boulders. The other thing is that the entire asteroid surface is extremely black. It's only 4% reflectance. So these images don't convey that very well because you're seeing kind of a light gray scale with, brighter rocks on top of darker rocks. But in reality, the whole asteroid is probably the color of my background screen more so than what you see in these images. Now, the reason that we see these little boulders and rocks on top of each other is that we know, of course, material is continuously being delivered to surfaces all over the solar system. So you do have tiny meteorites and things that are landing on the surface. But also we found out that as this body is rotating, it's getting superheated on the sun side and then cooling off rapidly on the dark side over a 4-hour period. And so a lot of these rocks have fractures in them. And we actually saw evidence of particle ejections. And so what we think was happening is that these rocks are being superheated and cooled continuously every 4 hours. And as they crack apart, you're getting particles thrown off of the surface. So this was not a very hospitable environment and not exactly what we were hoping to find when we got there. But, continuing on in terms of the sample site selection criteria, the other one was whether or not it had science value. And one of the first things we saw on approach to the asteroid was what is called the 3-micron feature. It's really 2.7 microns, but this is a hydration feature. It's basically evidence that you've got clay minerals on the surface that at some point in the past were exposed to water. And so there's OH and water basically down in their structure. And this is very similar to some meteorites that we see here on Earth, particularly the CI and CM class meteorites. So again, these carbonaceous meteorites, but there is evidence that there was water in their past. So we saw this as soon as we got to the asteroid. It was present everywhere on the surface. So from that perspective of potentially having had past water, any place on the surface was good. The other thing, of course, of interest was, as I mentioned, organics, and that's around 3.4 microns. And what we found is that there is an organics or carbonate band at 3.4 microns, again, all over the surface. The exact mineralogy varies. So some of them are carbonates versus organics, but basically the whole surface was a good location to sample. The only other difference we found from one place to another is that most of the surface is fairly bluish, really black, but again, slight loose slope, with the exception of some of the younger craters appear a little bit redder. So in the case of Bennu, we think that the newer surfaces are slightly redder. So from this, we mapped out the full surface, and this is actual data. This is a combination of imaging and the LiDAR data, so our shape model. Our shape model has millions and millions of facets. It's down to the centimeter level, but this was used because we needed to do this to understand the surface. And in this particular case, this is near a big boulder, and you can see kind of when the model takes over, it goes from that rocky look to a little bit smoother, and there's no information underneath the bottom of the boulder there. But now the video is going to zoom across, and we're going to go towards a crater. It's a little dizzying, but you can see that nowhere on the surface at the centimeter level is smooth at all. And some of those bigger white rocks that you see in this image are the size of about a house or a passenger van. So again, very, very rocky surface. So this meant we had to rethink how we were going to do our sample return a little bit. From looking at that full map, we came up with 4 potential sample sites. So we started from dozens and we kept ruling them out. And ideally, the engineering team would prefer it to be near the equator because that's easier to get to, but that's not where our best site was. So our 4 sites had nicknames after different birds. We had Nightingale Crater, which is the first one on the left there. That's kind of the biggest crater. It's also one of the redder sites on Bennu, but it is surrounded by these big boulders. Kingfisher, Osprey, which is much closer to the equator. Again, fairly smooth area, though it does have that big boulder on the edge. And then Sandpiper, which was a fairly smooth area, a little bit less cratery. So of these, Nightingale became our prime because it had the biggest clear area, but it is not at a low latitude. And our backup was Osprey. So if we attempted to sample at Nightingale and it didn't work, then we would potentially go back and we could use sample site Osprey. So one of the challenges we had was that when we proposed this, we planned on having a 50-meter area that was clear of any boulders. And that's what that looks like on our shape model. We didn't have those. The best we had was about 8 meters across. So this was like trying to sample in the middle of a parking lot between parked cars and buildings. A little bit more of a challenge than we anticipated. But we did have a contingency plan for this, and that was something called natural feature tracking. So what we did was we took that very complicated shape model and that was fed into the onboard computers. Because even though this is a near-Earth asteroid, there is a time delay. We could not drive the spacecraft down. It had to be done autonomously. So the spacecraft was using its navigation cameras to identify those boulders relative to the map and basically move itself to try to center in the crater. So now I'll show you how well we did. On the left, you're going to see the SamCam, which is looking down the sample arm. On the right, you'll see NavCam, which is one of the navigation cameras, which again was looking a little bit off to the side for those boulders. And in the middle, you'll see the map that shows you where we are relative to those. And so you see the sample arm on the left. These are not movies. These are actually separate image frames, so it'll be a little bit jumpy. But you can see from the red square in the middle of the orange circle that we were coming down pretty close to the center. So we were able to avoid those big boulders off to the side. And what you'll see is after it touches on the SamCam side, you'll see a big cloud of debris. And you can still see it in the navigation cam. So basically, we excavated a lot of material and you were seeing a huge cloud of debris get thrown into the air. And now the spacecraft is backing away. And so you can see from this navigation that we actually did very well in terms of landing pretty much in the center. So the design of the spacecraft was not to land and sit and make contact for a long time, but it was basically to barely touch the surface, low nitrogen gas to mobilize that loose soil, push it into the sample head, and then fire the thrusters and back away. So this is a still graphic that shows you how we did. So again, we had that 8-meter ellipse that we were using for our touch and go. And that's kind of mapped out here in the color region. So those red areas were the things we were attempting to avoid. Those were the boulders, and the green area, anywhere in the green area was a good place to sample. And what we ended up doing is we tagged to within 73 centimeters of the center, so less than a meter from the center. So it really worked extremely well. The natural feature tracking was a great success. So again, we picked this particular crater because it was among the youngest features. It was spectrally redder than the surface, but it was mid-latitude, so we weren't sure how well this was going to work. So really, this was spectacular success that it worked as well as it did. The other thing is it didn't get quite as hot as the equator, so we had better spectral information about it, and it probably was slightly less processed. So in the end, this was the great location, and we actually were able to basically bullseye right on the crater. But this wasn't the only challenge we had. So I'm going to show you 2 videos here. One is on the left. This is what we expected to happen. So again, we expected to make contact. That was supposed to be triggered by accelerometers. It would wait a few seconds, fire that nitrogen gas. That would move all the rocks, push it through our sample head, which looks a little bit like a car filter, and then fire the thrusters and back away. And I'll play that again so you can see again, the sample head looks a little bit like a filter. And the gas comes down through the middle and out the side. So that pushes any rocks that it lifts up basically into the center of the sample collection mechanism, where there's a flap to keep it in. Now, what really happened looked like this. We never actually registered contact on the surface. Instead, what happened was a timer went off. So basically we knew how long it should have taken us to get to the ground. And when that didn't trigger the sensors, an automatic timer went off instead. That fired the gas and then backed away. And so what happened is we essentially kept sinking. So we're sinking, we fired the nitrogen, we're still sinking. And then the thrusters are what stopped it and pushed it out. So the entire surface was much, much softer than we expected. We did not hit hard rock. It was much more like hitting a children's ball pit where, you know, there is no surface, you just keep sinking in. So luckily we had that backup timer specifically in case the surface was different than we expected. So from this, we had a requirement to pick up 60 grams of material. And depending on what it was, if it was rocks or more loose dust, we could pick up to 2 kilograms. But we had to know if we actually got a good sample or whether we had to try again. And so we had 3 ways that we were going to do that. And the first was to look at the sample head itself. Let me get to the next one. And we have these little witness plates around the edge. They kind of have little, almost like steel wool fibers in there that can pick up particles. So we would look at them and see if there was anything in there. The second was shining sunlight through the side to see if material was in there. And that's what this view is here. And what you can see is there's so much material, it is continuing to fall out. And this wavy line towards the middle is actually the edge of that mylar flap. And what happened is that there were some pebbles that were holding it open and keeping it from closing all the way. So this image, first of all, told us that we definitely picked up a lot of material, but we were also somewhat concerned that if we did anything else, we might, you know, continue to lose material. So our third test was to actually take the whole spacecraft and spin it. And so with the arm extended like this, we would be able to measure the change in the moment of inertia from before sample and after sample. That's only good to about 90 grams. So we would have to have picked up 150 to meet our 60-gram requirement and know that we had it in there. But once we saw this, we decided not to do that test because we did not want to spin the spacecraft and throw even more material out and potentially lose it. So the decision was made at that point that we should stow the sample. And that led to the next challenge, which was we were now going to be dumping this dust all over the place. So we wanted to watch and make sure that the sample return canister actually closed cleanly because we were worried that if we were dropping pebbles, they could potentially prevent it from closing. So I'll play that again because if you look closely, and it depends on your screen, you'll actually see little bits of dust continuing to fly off while we're doing this. So basically taking that sample head, putting it over the deck and then putting it down in, there was still material falling off everywhere. The other thing to note that is what our sample return canister looks like. So on the top part there, that white material is a heat shield designed to ablate at some level as it enters the atmosphere. And then the bottom is thermal protection material. And so this was all designed for Earth entry at very high conditions. But of course, we wanted to make sure that it was closed when we did this. So this was our stow cam, which was entirely put on the spacecraft for this purpose, which was to watch this happen. So that was pretty cool. So what happened on Earth return? So this was September 24th. This is a video showing what we expected to happen. So the spacecraft actually took a little while to come back around to connect up with Earth at the right point. The capsule was released, and then it goes screaming into the atmosphere. Because it is coming in awfully fast, that whole capsule heats up to about 5,000 degrees. So it's not insubstantial heating up. And then we had both a drogue chute and a main parachute that would slow it down. And then it would land in the Utah desert in the Utah Test and Training Range, which is an Army base, before eventually going on to Johnson for curation. And of course, then we'd get the sample out. So for any of you that watched this actual event on September 24th, it was a bit of a nail biter to watch. So this is first of all, a view from the spacecraft as we released the canister, which is pretty cool. You can actually see the different points on the bottom of it, and off to the right is the Earth there. So that was the last view that we had as it got released, which is pretty neat. So after that, it was nothing that we could do except wait to see it come down in. And so it's landing in the desert. The image on the left shows the kind of a far out view. you can see there's kind of patchiness in the soil, and that's because it had rained a couple days before. So there actually were some muddy patches on the ground. We were a little bit worried about that and where it was going to land. And you can actually see the parachute off to the side there. So that's where it got cut as it came in and it landed off to the side. The one interesting thing and really nice thing about having somewhat softer soil is that it landed directly on its nose cone and it didn't fall over. We expected to see it kind of fall over, roll around a little bit, and the ground was soft enough it didn't. It just stuck the landing. So picture perfect landing. But remember back to what I was showing you where the bottom, the heat shield was white and the top part was orange. Now the whole thing is very black, very carbonized. That's what we expected to happen because of those blistering temperatures on the way in. And so that was to protect this. But if you watched any of the collection where they picked this up and they brought it into a temporary clean room on the test range, everybody that had white gloves on, they quickly got black, right? And that was all this carbonized material on the outside of the sample return canister. So once we got it into that clean room, they took off that heat shield. That's all the avionics equipment and electronics on the top. And then it got taken off so you could get to the sample head. And this is what I was talking about previously. So this is not open yet. This is still just looking at the bottom of the sample head. And you can see these witness plates, which again, have little bits and particles stuck in some of them, as well as the fasteners holding it shut, including the center ones. This is all material that came off of Bennu that was still left on the inside. You can see there's kind of dust everywhere. If you look closely, you'll see some pebbles in here. Those are the pebbles that were holding the flap open. So some of the material did fall out because the flap was held open, but we still had a lot that was caught in there. And then curation in Johnson in the clean rooms in very small glove boxes basically sat there with tweezers and brushes, picking up every single little dust particle, every single little pebble, and sorting them into different samples. Now, before I get into what we found, we did have some predictions of what we would see in this sample. And this is based on what we saw from that remote sensing data. So basically the spectrometers. As I mentioned earlier, we expected to see hydrated phyllosilicates, clay materials. We also saw a lot of evidence of iron oxides and sulfites. So magnetite, goethite, troilite, very faint signals, particularly in the visible near IR. But magnetite really stood out in the thermal IR as well. So we expected to see a lot of iron bearing minerals. Again, as I mentioned, we saw carbonates of several kinds and probably organic compounds. The one thing we couldn't see were other sulfides that are not spectrally active, but they were inferred from the meteorite samples. So this was our prediction going in on what you would see. Now, we had a requirement to collect 60 grams. In the end, we got 121. So just from before we even took the sample head off, you can see there's dust all over the place. That was very carefully brushed up. That was 1 gram. A lot of that got sent out for quick look analysis to the science teams. 70 grams, while we still couldn't get the canister open. So 2 of our fasteners stuck, but this is what they were able to get from on top of that flap and from those pebbles that were stuck and reaching in. Once we got the top off, we got another 50 grams. So in total, we had 121.6 grams. So you might be wondering, what do we do with all this? This is very carefully curated and cataloged at Johnson as part of their astromaterials group. And the samples that get sent out around the world. So there's a slew of different analyses that are going to be done, all different types of spectroscopy, spectrometry, microscopy, everything you can possibly think of. The samples are being sent out around the world to various locations where our COIs are, as well as we are sharing samples with our colleagues at JAXA as part of an agreement. They also shared some samples from Hayabusa. But the important part is that 70% of the sample is just going to be basically archived. It's not going to be sent out at this time. And that's because there's going to be future experiments, things we haven't thought of yet. People will propose for those samples, just like we do now with the Apollo moon rocks and other samples. So this is a suite of extensive analysis that'll be done now, but then again, 70% will be available for proposals for the future. But, the reason that we wanted to do this is because you can have far more sophisticated equipment in laboratories than you can on a spacecraft. So again, we're trying to tie together what you could see from a telescope here on Earth to what we could infer from remote sensing around the asteroid to what you'll get out of the labs. So really, it's a nice experiment of tying those three scales together. Okay, so back to what we predicted. We predicted the phyllosilicates, the iron sulfides, magnetite, carbonates, organics. Fourier transform infrared spectroscopy in the lab found phyllosilicates. Again, not a surprise. That was one of the big things that we saw all over the surface. So not too much of a surprise with that one. They also saw lots of evidence of these iron-bearing minerals, in particular the iron sulfides, various contents of nickel and other things in them, different morphologies, but again, a lot of evidence of these. Again, the pebbles, you can see the pebbles have a lot of little variations in them. So even though it's, a rubble pile, even within every smaller rock, you see a lot of different variations. Lots of magnetite, different, again, morphologies. They're seeing plaquettes, they're seeing evidence of framboise, they're seeing some that are etched or weathered, which is really interesting. Again, that means that some of this material was probably very old and was part of the original parent body. So very interesting material that we're seeing from the scanning electron microscopes. Carbonates. This one was interesting because carbonate features can have very similar spectral signatures in the near IR. So sorting out exactly which one you have can be tough, particularly when you're looking at a very dark surface that has a lot of opaque material on top of it. So we were pretty sure there was calcite and dolomite, but possibly other ones, and that is exactly what they're seeing. They're seeing also brunerite and some other minor minerals. So a lot of evidence for these different carbonates on the surface and in the sample. And then we did see evidence of organics, but they also saw one thing we didn't see, which was the sulfides we expected and phosphates. And phosphates we didn't predict at all. So that was a really interesting finding. Again, evidence that there was aqueous alteration on this body. So we do think that Bennu, as I said earlier, formed in the main asteroid belt from the collision of two different asteroids. It made a whole family of smaller ones, some of which eventually got thrown out of the main belt and became near-Earth asteroids. But it does mean that those parent bodies were probably pretty big. So similar to Ceres and stuff, there's evidence there was a lot of potentially water and aqueous alteration on these parent bodies. So in terms of, can you go see these samples? You can actually go see one. Click this. There is one that's on exhibit at the Smithsonian, and here's that pebble up close, but you're going to actually see a scanning electron microscope scan across this particular little pebble. And it is really quite interesting. You can see all those tiny inclusions. You'll see different minerals light up. You'll see a couple somewhat roundish inclusions and big ones. You'll also see a lot of little fractures. So this is what we were saying about, the surface has a lot of thermal processing that goes on, but we also found that some of these small pebbles possibly broke when they were collected. So we have at least two that fit together. And it's evidence that these have a lot of fractures in their structure. So they are very crumbly. So it's just really neat to watch that and just see that morphology change as you step across it. And I think it'll repeat. There it goes. And so this one won't be ground up or taken apart in any way. So all the information we have is from this scanning electron microscope. And there are different wavelengths and techniques that were used. So we do know that some of those are the organics that are popping up as well as some of the other minerals. And I'll just let this finish playing through. So a lot of this analysis is ongoing. Some of the samples are still being sent out for the prime teams. So there's still a lot of work to go. You're going to see a lot of papers coming out. There were a lot of presentations at LPSC, the Lunar Planetary Science Conference, but you'll continue to see them as they're coming out. But one thing I want to talk about was that we made it look simple in a lot of ways. It was a completely successful mission, but we faced a lot of challenges actually getting this to work. And that was right from the very start. And so during build and test, we had a number of catastrophes. The first and foremost, of course, was the death of our original principal investigator, Mike Drake, who really was the driving force behind this mission. So that was a great loss to the team. We also had to face a lot of politics. So we had government furloughs, we had a Canadian austerity movement. So we had to fight the usual budgetary challenges. But we also had a huge number of natural disasters. At the beginning of the project, we had a large earthquake in the DC area, which luckily didn't destroy any hardware because we were not that far along yet, but it was a little bit unusual. We also had a fire that destroyed my instrument. So my instrument is visible on near-infrared spectrometer. And to make sure that it's extremely black, even in the near-infrared, we had very specialty coating that we used on the inside of the instrument. And it's an anodized coating. It was only made by one person in the world, out in Hollywood, California. And so our flight box had been coated and was ready to come back. And so we had sent our spare out. We were waiting to receive it. The flight went back and we didn't hear from him. And so we started trying to find out what was going on. And one of our engineers was looking for an alternate phone number because he wasn't answering. And he found this picture in the news, which was a cloud of toxic chemicals over Hollywood, California. It turns out that the plating shop actually had a fire and burnt to the ground with our flight box sitting on a table. And unfortunately, he had already received our flight spare and it was sitting next to it on the table. So our box is in the lower right here. That's actually all aluminum. It melted. So that'll tell you how hot the fire was, about 1,600 degrees, I think we estimated. So that was a real challenge. We had to basically start from scratch and get that up in a hurry to still meet the planetary launch window. A different instrument had a blizzard that got in the way of them building their instrument. There was also a train wreck that destroyed part of another instrument, plus just getting parts in on time. So there were a lot of challenges to everybody getting to the launch pad on time. And luckily we did. But once we were at the launch pad, we still weren't safe. While we were getting ready to launch, we were going through the last integration and test, and everything was loaded into the rocket and on the fairing when there was a hot fire test at the pad nearby and it actually exploded. So that was a scary moment. Luckily, nothing was harmed over on our pad, so that was a good thing. But even after launch, we had a number of challenges. There was fires in Canberra while we were approaching Bennu, so we lost our DSN coverage. We also had a big US internet outage that took out the DSN during a different maneuver. Of course, we had the unexpected surface at Bennu that made it challenging to do the sampling. There was also a big bomb cyclone that hit during another critical event, a blizzard out in Colorado. Nature was not on our side during this mission, but we pushed through. And then, of course, during and after the sample return, that rain in the Utah desert gave everybody a little bit of pause because we did not want that sample return canister to land in a puddle and potentially get contaminated. And if you were watching it, you actually would have noticed that the landing didn't seem to go exactly according to schedule. It was actually going fast. And that's because the drogue chute did not open. It deployed late. Luckily, the main parachute was able to slow it down enough that we didn't have a catastrophe and a hard landing, but that did not exactly go according to schedule. And then, of course, once we got it to curation, 2 of the canister fasteners did not want to open, and that actually delayed us for quite a while they made a new tool to get it open. So, we had a really remarkable team, and I can't say enough about the engineers and scientists involved in this mission because we had to overcome a lot. And in the end, everything was a complete success. All the instruments worked, sample return worked on the first try, the sample got back cleanly, and we now have a lot of data and material to work with. But we're not done yet. So OSIRIS-REx is now OSIRIS-APEX. So the mission is going on to a new target. We proposed to the NASA Senior Review for an extended mission, which was accepted. And we are headed to near-Earth asteroid Apophis. So Apophis will have a close encounter with the Earth in 2029. You may have heard about this before. That was the one that they were concerned might potentially hit the Earth. It passes between the Earth and the Moon, so it is an extremely close pass. And it will be visible to the naked eye from the Eastern Hemisphere. So that's going to be quite exciting. It's going to be in the news. Everybody's going to be watching this flyby anyway. but our spacecraft will be zipping around and catching back up to the Earth in time to meet Apophis, basically just past this close encounter. So we will be mapping out the surface. Because the asteroid is coming so close to the Earth, we expect that it's going to be tidally pulled around and distorted. So we think there's going to be changes in the surface just from the Earth pass. So it's going to be interesting to see how soft Apophis's surface is compared to, say, Bennu, and if we see a lot of evidence that there were rock slides or mass movement just from the tidal forces from the Earth. We will get into orbit as we did at Bennu. We're going to map out the surface as best we can. Bennu is not the same as Apophis. So Apophis does not rotate nicely like Bennu did. It tumbles. So mapping it out is going to be a little bit more of a challenge. You can see the shape model that we currently have. Again, we don't know a whole lot about it. It does seem to maybe have two lobes, a little bit peanut shaped, but we'll see what it looks like when we get there after the Earth's close approach. And then after we do all of our mapping, we're going to do something similar to what we did at Bennu. We can't return another sample, but we can get down close to the surface and fire the thrusters and see if we can make another crater. So we're going to see if we can change the surface as we did on Bennu. In terms of the current spacecraft status, so to get to Apophis, we're going to have to do some risky maneuvers. So first of all, the status of the instruments. When we did that sampling at Bennu, we threw up that huge cloud of debris. It coated everything on the spacecraft, including the instruments. So most of the instruments do have a dust coating on their optics, so it's a little bit less throughput than we had before. But luckily, Apophis is much brighter than Bennu, so that offsets it. But Apophis is much brighter than Bennu, so that's also a little bit of a challenge for the instruments. So they were designed to look at something with about a 3 or 4% reflectance. Apophis is about 30%. So it's an order of magnitude brighter, but we can handle this in operations, basically much shorter integration times, and we're calibrating out the effect of that Bennu dust basically on all the optics. But we also have to do these tricky maneuvers I mentioned to catch up to Apophis. So to get there, the spacecraft is basically in a Sun-Earth orbit right now. We're going to be doing 7 perihelion passages where we go down to 0.5 AU. So that is awfully close to the Sun. The spacecraft was not qualified for that. It was qualified for a 0.8 AU, so a little bit farther than Venus, whereas we're going to be going in closer. So the spacecraft gets quite heated up. We're basically requalifying the spacecraft in flight. We've adopted what we call a fig leaf configuration, where we turn the spacecraft and hide all the sensitive components and instruments behind the solar arrays. And we've already done one of these. We did one late last year, and everything worked fine. All systems are nominal. We're on our way to Apophis, and we're going to approach in April 2029, and we'll pass it actually, and then we'll do the arrival and parking orbit shortly thereafter. So everything is going really well on the spacecraft right now, even though it was not designed for this. We will be actually having another one of these perihelion passages later this year, and then we have our first Earth gravity assist next year, which pushes us into a slightly different orbit. So we're basically using a combination of these Sun passes and Earth passes to line us back up to approach at the same time that Apophis gets here. And with that, I will stop and take any questions. And I'll stop sharing so I can actually see you.
Thank you, Amy, for this fantastic talk. This is just, it was spectacular, not only the scientific insight, but just to be taken in the journey that you all lived through. And it felt like, you know, I was reminding me my time on JWST when everything was happening. But in spite of that, the teams are resilient. They deal with all the stuff that is thrown at them, and the missions are so successful. So congratulations to you and the team for such an amazing success. And we're really looking forward and seeing the next step. I will take privilege to ask you the first question because I'm very curious. Can you tell us if you saw anything that you didn't expect out of your sample analysis?
Yeah, I mean, there's been a few. I mean, certainly those phosphates, some of the more volatile things, you know, we weren't really expecting. So there's a lot of analysis going on now. And I think there's a series of papers coming out that are going to talk about the more recent work. But the phosphates were a big surprise.
And what do you think would be the origin for those?
They're still working it out. Of course, the folks working the sample are, I'm trying to think of the right word. They're extremely meticulous, right? And so the first thing they do is they assume anything unexpected was contamination. So they have to rule that out first. And so they're very careful in how they handle the samples. They look at the isotopes to make sure it isn't terrestrial contamination and so on. So it really is a very comprehensive and piecewise approach to determining where it came from. So I think they're still working on the origin for everything.
Okay, fantastic. So let me read, we have a bunch of questions in the chat, so I will now read them. So Kirby Ramion is asking, I'm curious about the compressive and tensile strength of Bennu's regolith boulders. I understand that the Amorphous has probably only 5 to 50 tensile strength. What would you estimate Bennu's strength at? And what more common material would you compare it to? Thank you for a fascinating talk.
I don't know the tensile strength off the top of my head. I do know the thermal inertia was not what we expected. So we expected the boulders to be pretty, I'll get it backwards. What we found was that the boulders were the opposite of what we expected, which indicated again that they were either very porous or very soft material, whereas the spots we thought would be more like loose regolith were probably a little bit more concreted in place. But in general, you saw the sampling, everything was extremely soft. So I don't think there was a lot of strength to it. But on the other hand, the initial gravity modeling showed that there was some internal strength of the asteroid. So it was very soft, very rubbly, but there still was some cohesive force to it.
Thank you. So the next question is from Jean-Luc José. So it scrolled away. How many cameras have been used on the probe and spacecraft to monitor and visualize all the steps in the mission?
So we had a lot of cameras, actually, quite a lot. The main imaging suite was actually 3 separate cameras, Polycam, Mapcam, and Samcam, but we also had nav cams and we had a STOCAM. So there were quite a lot of cameras because we were trying to look from both very near and very far. And so we needed a camera that could look when we were far away. We needed ones that could look when we were much closer, plus actually looking at the spacecraft itself. So I think in total we had 5 or 6, 7 cameras. It was quite a number, and some of those have not been used for scientific purposes. For example, STOCAM, because it was designed to look at the sample return canister, but now that the canister is gone, we can look right past it. And so we can use it to monitor other stuff on the deck, but we can also now see to space where we could not before.
Fantastic. So we have a question from William Wall. How will you do the sample collection and return differently from Apophis given what you learn in Bennu? You answered that.
Yeah. Apophis, we can't do a sample return because we no longer have a sampling arm. But we can actually at least get near the surface and excavate a crater, but we can't bring it back and we won't have any fuel at the end of the mission.
But there is a follow-up question that says, how would you redesign an asteroid sample collection given what you have learned from Bennu?
Yeah, that's actually a good question, because there's been a lot of things proposed over the years, including attempting to anchor to a surface, to scoop it up. The Hayabusa mission, the first one shot a projectile to basically push some of the material out to space. I think what we saw on both Ryugu and Bennu is that the surfaces were very soft, much softer than we expected. So anytime you send a projectile or touch them, they crumble. So I think if you were going to go back to a rubble pile, you might rethink what you expect that surface strength to be. Other asteroids, a stony asteroid might be different though. So I think probably you'd want to look more at material properties after they've been through extensive heating and cooling and bombardment. And I think we were not necessarily thinking that. We were expecting a lot more hard rock than we actually encountered.
Thank you. So there is another question from Kirby Ranian asking, to prepare for experimental crater excavation at Apophis, do you have microgravity parabolic flight experiments planned?
We don't have any experiments planned for Apophis. We did do those for Bennu. So that sampling mechanism we tried in zero gravity or microgravity, as well as just in the laboratory with different materials. So we did do that for Bennu, but as an extended mission, we have much more restrained funding and time, so we won't be doing any of those sorts of experiments.
So thank you. Another question is, could you please elaborate on the procedure followed to prevent forward and backward contamination?
Sure. So for the contamination control was a huge thing on this mission, because we wanted to make sure that we knew exactly where everything in the sample came from. So in terms of contaminating the sample and or the surface, everything was required to be kept extremely clean. We also had to archive samples of every material that we used. So if you used any sealants or glues or lubricants or anything like that, we had to archive part of the sample. We even archived some of the hydrazine used in the thrusters, so that if there was ever a question, we could go back and compare it to the archived sample. So that was all designed to make sure that we did not contaminate the sample. In terms of bringing it back to here on Earth, as soon as the sample was on the ground, it was basically secured in a clean room and then put under nitrogen purge and immediately brought to Johnson and kept under purge there. So none of the samples are basically allowed out into the atmosphere or any of that. Basically, mostly concerned with contamination on the sample. There's not really any risk of contamination here on Earth, but nonetheless, we wanted to make sure we kept everything pristine.
Thank you. One last question from Philip Nicholson asking, you mentioned carbonates and organics as potentially present, and you show some data on the former. Did you also find organics like CH material?
They did. They found quite a lot of extensive organics. I don't know exactly which ones they were. I think some of them might have been Carrageen-like, but I don't know that that's what they are. But there are folks that work specifically on organics that are looking at the samples now. But yes, we did find organics.
Very interesting. So you realize that with this wonderful talk, we booked you already for 2029 to tell us all what you found when you go on Apophis. And at this point, I will just thank you again. This was a fantastic talk, great presentation. And thank you so much for your time and for sharing it with us.
Thank you. Thank you for having me.
And thank you all for listening. Goodbye.